All right, welcome back, everyone. This is part two of today's videos. The first one was on parametric equations. This one on vectors. Vectors, for the most part, are really just parametric equations. So um, vectors describe motion. Um, so we're going to do vectors in both 3 dimensions and 2 dimensions. Most of our stuff will be in 2 dimensions, but it works in 3 dimensions. This is a pretty funny eye there. So here's just a way to write a vector. R is the position vector, and it's just f of ti plus g of tj plus h of tk. We did a little review on vectors in class, so hopefully we're all good with this. So anyway, vectors really are just parametric equations, especially when you're in 2 dimensions. Notice we just have some function of ti, some function of gj, and some function of hk. Sometimes we actually write this x I plus yj plus z. Okay, so we just call them x, y, and z. Most of ours will be in 2 dimensions, x and y, but I just want to show you that it can carry over to 3 dimensions also. So some simple math with the vectors, and then we'll do the motion part of it, which is the more important piece. So finding the limit of a vector is very simple. It's finding the limit of each individual component of the vector. So here's the limit as t approaches a of r is equal to each individual limit. It's very straightforward. You're just finding 3 different limits. So your answer would be something like 3i plus 2j plus 4k, whatever those limits are. So limits are very straightforward. I'm not even going to do an example. They're pretty straightforward. Just take the limit of each component. If someone asks you if a vector is continuous, it's the same way, right? So it's continuous at t if the limit is equal to the functional value. We won't really do much with continuity with vectors, but I just want to point it out that it works the same as it would. We're going to do derivatives and integrals. So derivatives are very simple. Vectors are actually really, really simple. Derivative of a vector is just taking the derivative of each individual component. So here I have written r prime is equal to f prime I plus g prime j plus h prime k. Or if there's only 2 dimensions, just the I and the j. I'll do an actual integral. I'm going to come back to the motion there in a second. Integration works the same. So if we're going to integrate r, we just integrate each individual term. So let me do an integral for you. A derivative will work exactly the same. You're really just ignoring the I, the j, and the k for a little bit. You're treating each one as a separate entity, and then you're putting the I and the j and the k back in. So if I'm going to integrate this thing, the first term is 12t cubed. So we're going to integrate that. It will be 12t to the fourth. I'll write it out this way. 12t to the fourth over 4i. And then we got 4e to the 2t. So the integral of e to the 2t is going to be e to the 2t divided by 2. So when I take that 4 and throw that in there, 4 divided by 2 would be the 2. And then this would be t plus 1. Or you think about it this way, 1 over t plus 1 is just going to be a natural log of t plus 1. And yes, I know I forgot that j there. And again, we can put the I, the j, and the k back in there at the end. And then we're going to integrate from 0 to 2. So we're going to do each one separately. They're separate entities. We're going to combine like terms, for lack of a better term. So we plug the 2 in, 2, 4, 8, 16, 4. So that's going to be 48i. Plug the 2 in here. It's 2e to the fourth j plus the natural log of 3 times k minus, now we're going to plug in the 0. So 0i plus e to the 0 is 1, so 2j. And then the natural log of 1 would be 0 plus 0k. And now we're just going to subtract the individual components, or the like terms, for lack of a better term. 48i plus 2e to the fourth minus 2. Those are those like terms there. J plus the natural log of 3k. And there's my answer. So integration, limits, derivatives, all very, very straightforward, just term by term by term. The main focus of the vectors is describing motion. So we've described motion before. So velocity, acceleration, speed work exactly like you would expect. They're pretty much just parametric equations. So we're going to go back to 2 dimensions and kind of compare them to parametric. So I just have some examples. So here's kind of the two different types of problems you'd see. So here we have a position vector, 2t cubed minus 3t squared j plus t cubed minus 12t j, I, and then j. So I'm going to ask all the similar types of questions. I'm going to move this here. Let me come down here so you can see both. I'm going to erase this one. Give me a second here. Oops. Get rid of this. All right, now you can see both. So equation of a tangent line. So tangent line, when t equals -1, we need slope, and we need a point, right? So remember slope. So in essence, what we're doing is parametric. So I have this function. We're going to call it RT equals 2t cubed minus 3t squared I. This is the position of this vector. Remember, this is like saying x is 2t cubed minus 3t squared, and y is t cubed minus 12c. So keep this in mind, that these parametric equations are going to help us solve these problems because they really are parametric equations. So when I say find the equation of the tangent line, I need the slope, which is dy dx, which from parametric, I hope we remember, is dy dt over dx dt. So dy dt would be 3t squared minus 12. And dx dt would be 6t squared minus 6t. The question was, find the equation with t equals -1. So when t equals -1, we're just going to plug that right into there. We're going to get -9 over, let's see, 6 plus 6, 12, so -3/4. Now we need a point on that line, on that equation, which is just the point when t equals -1. So we're going to plug t equals -1 right into there to get my point. So x would be, let's see, -2 plus 3. And y would be -1 plus 12. So it looks like 1 and 11. So we get y minus 11 equals -3/4 times x minus 1. There's the equation of the tangent line. So treat them like parametric equations, basically. The next part of that question is find the points where the horizontal component has 0 velocity. So this was my position function. So my velocity function is just the derivative of the position. Just take the derivative of the vector. So it's going to be 6t. We've already done the derivatives over here on the other side. You can look 6t squared minus 6t I plus 3t squared minus 12j. So that would be the velocity vector. And the question was, find the points where the horizontal component has 0 velocity. The horizontal component is my motion this way, so it's x. And just when x is 0, basically. So 6t squared minus 6t equals 0. Factor out of 6t. And we get 1 minus t equals 0. So that's 0 and 1. And then the third part of the question is find the speed when t equals 1. So speed, remember, is the magnitude of the velocity when we're dealing with vectors, or it's the absolute value of the velocity. So my velocity vector, remember, is right here. Right? So the speed becomes the magnitude of that vector. So think about Pythagorean theorem. This vector, whatever it is 6t squared minus 6t in the x direction, and 3t squared minus 12 in the y direction. So we do the little Pythagorean theorem. 6t squared minus 6t squared plus 3t squared minus 12 squared. That would be the speed. I'm not going to plug in the 1, although plugging in 1 is pretty easy, I guess, huh? Because we get a 0. So I'll do it. Go ahead and do it. I was not going to do that math, but it's pretty simple. Plug in the 1. The other one is 3 minus 12 is -9. 9 squared is 81. So it looks like the speed is the square root of 81, or 9. So speed is the magnitude of the velocity. So think Pythagorean theorem. And then this will look the same. I'm going to give you the equation as a position, or as a vector, and ask you some questions about the position. So let me rewrite it down here so we can see it. I'll just rewrite it on my paper here. Sorry about this, so you can see it also. My velocity vector is 1 over t plus 1 times I plus 2t times j. First question is find the position at t equals 1 if, nope, sorry, that was not the question. Let me try that again. Find the position vector. So it was just find position vector. If r equals the natural log of 2I when t equals 1. And the second part is total distance traveled, which we might remember from chapter 8, I think. Total distance traveled, t equals 0 to t equals 2. So the position vector is just the same as it worked before, right? We have the velocity vector, so the position vector is the antiderivative. So the position vector is the integral of 1 over t plus 1, which is the natural log of t plus 1 times I, plus t squared, 2t squared over 2, so t squared j, plus some constant, right? So we have to find that constant. We have an initial position. R is the natural log of 2 times I when t equals 1. So t equals 1, we get natural log of 2 times I. We're going to plug in the 1 now. Equals the natural log of 2I plus, plug in a 1, j plus c. These are going to cancel out. Yeah. We're solving for c, right? So c is equal to negative j. So now we plug that back in and we get the natural log of t plus 1I plus t squared j minus a j. These are like terms. Typically, we would have both. The I canceled out on that one. So we're just going to combine them. And we get natural log of t plus 1I plus t squared minus 1j. Integrate, find the constant. And the last question is total distance traveled. So we go back to chapter 8. Remember, total distance traveled is just integrating the speed, right? Integrating the speed or integrating the absolute value of the velocity, well, to make all the velocity positive to make the total distance traveled. So we're going to integrate the speed. And remember, the speed, like it was in the last example, is the magnitude of the velocity vector. So we were given the velocity vector in this problem right there, right? That is the velocity vector. So we're just going to go 1 over t plus 1 squared plus 2t squared. That would be the speed, right? So we're integrating the speed. I'm going to stop there. You can just dump that in on your calculator, and you'll have an answer. So that's it for vectors and parametric equations.